So now I want to very briefly discuss the issues of insertion and deletion in a B tree. And the main issue that happened when we are doing insertion and deletion is that we have to remind ourselves that every node in a B tree, the number of keys in that node has to be greater than or equal to t minus 1 and smaller than or equal to 2t minus 1. So when we are inserting a key into a node, we could violate this property here, right? So if a node is already full, as in it has the maximum number of possible keys, and we want to enter a key there, it's a problem. When we are doing deletion, we could cause this problem here, that we have a node that has the minimum possible number of keys, which is t minus 1. Once we delete, it goes to t minus 2, and that violates the properties. And what we really need to do is either split nodes in the case of insertion. So if we have a node that has that has the maximum number of keys, we need to split it and create a new node so that we don't have a problem inserting. And if we have deletion and we go into a node that has smaller than the smallest possible number of keys, we have to merge nodes together. Okay, so if I want to first talk about insertion, again, we're not going to talk much about deletion here, but if I talk about B tree insert, and it takes two parameters as input x and k, so I want to do insertion in the subtree rooted at node x, and I want to insert the key k. So whenever we call it the first time, if we want to insert the node or the key into the tree, we basically call it on t.root with key k. Okay, so when we are inserting a key into a node, one of the things that might happen is the following scenario here. So for example, imagine that we have, let's say, L and Q here, and think about it, for example, that from the pointer between L and Q are keys, and the pointer there. Okay, actually, let me not take Q here. I take something L and Z, let's say. Okay, L and Z. And suppose between them, and let's assume that we have T equal 3. So for this node, the new node that's between L and Z, to be full, we have to have 2 times 3 minus 1, which will be 5 keys. Okay, so if T equals 3 and we want it to be full, then we have to have some 5 keys in this node. So L, we can have, let's say, M, N, O, P, and Q here. Okay, so if we have this situation and we want to enter a key, so suppose now we want to insert, the key, let's say S. Okay, so if you want to insert S, that S has to, we come to this, we first check this node and say, okay, S goes between L and Z, so we come to this node. Here we want to insert S into this node, but this node is full, right, because it has the 2t minus 1 keys, so we cannot do this, right? So what do we do here? That we have to split this node to allow S to be inserted into it. How do we split this? So what happened here is that I look at the median key in this node, and I lift it up to the parent node. So now I can put the O. So what happens here? That we have L, and we have O, and we have Z. And now we split this into M and N, and we have P and Q. And now this key here, this pointer between L and O points to M and N, and this pointer between O and Z points to P and Q. Okay, and now if you look at this, what happened here is that neither of these two nodes that have M, N, and P, Q are full. I can insert things into them now. Okay, so if I want to insert S here, now what happens is that I can come here. I say, okay, I need to insert S. S has to go between O and Z. So I come to this node here. S, I have P and Q. S comes after Q, and I can insert it into this node. So now we have PQS. It has 3 keys. It is smaller than or equal to 2t minus 1, and we have no problem. Notice that what happened here is the height of the tree did not change. Okay, we had the node with LZ and its child. Now we have the node with LOZ and its 2 children. So the height did not change. One of the things that it's important to point out here is that these nodes have changed. So the L and Z, this node has changed because we added O. The MNOPQ changed because now we have 2 nodes, MN and PQS. So all this is going to result in 3 disk write operations. Okay, because we need to update the information on the disk, and we have to update it with these 3 nodes. So this is just like disk read is an expensive operation, also disk write is an expensive operation, and in general we don't want to cause problems with that. Okay, now the questions that you might ask now is that once we put O with LZ, what if that node was already full? In other words, what if the node was, let's say, A, B, C, LZ, and we had this MN, O, P, Q, okay? And this was pointing here. So if I want to split the MN, O, P, Q, what's going to happen here? We are going to have the A, B, C, L, O, Z, and then we will have MN and the PQ here, right? And we will have this situation. But this is a problem because this node has 6 keys, and 6 is greater than 2t minus 1. So this is a problem. How do we solve it? In exactly the same way we solve all problems with these kind of trees. We solve it with red-black trees, with binary search trees. You just repeat the operation and go up now. So now what happens? I need to split this node to be able to do that. So we had A, B, C, L, Z. So now we split it into A, B, and LZ, and the C now goes to the C goes to the upper parent here, and now we have no problem. Okay, so the insertion works as we insert the key all the way to the in some of the in one of the leaf nodes. So we go to the leaf node, we insert it. If the leaf was not full, then we have no problem. We just insert it and we are done. If the leaf was full, then we have to split it and insert the key. Once we split it, the parent now might be problem because maybe the parent was full and we need to split that one. That's fine. We can go to the parent, split the parent, and insert. Now, maybe the grandparent was full and is causing problem. It's fine. We keep doing that all the way to the root, but we know that that path all the way from the leaf to the root, the length of that path is O of log to the base t of the number of keys. Okay, so the number of operations is logarithmic. So this is basically how insertion works, and it basically the amount of time it does is on the order of log n to the base t. Again, we need to compare two keys in the node, and a node can have on the order of t keys. The running time of insertion is O of t times log n to the base t. Okay, this is really the main idea of insertion in a B tree, and I'm not gonna write the pseudocode for it or anything like that. Now remember that you keep going all the way up to the root. At the end with the root, you can split it. Remember that the root has to have at least one key. So we can even split it and have fewer than t minus 1 because we can afford a root with one key in it. Okay, and this is the way we insert into a B tree. And again, the number of disk operations here is in the order of log of n to the base t. But again, for every node, when we are comparing the keys, we might be doing on the order of T operations. Okay. In terms of deletion, what's going to happen is when we delete from a node, we might now have fewer than T minus 1 keys. If you delete from you delete from a node and you have fewer than T minus 1 keys, what we need to do now is basically merge nodes together. Okay, so if, for example, if we have T equal 3, let's say, and the T minus 1 is 2, so suppose we have here M and Q, and suppose I want to delete Q from this node. If I delete Q from this node, I go to M, but this is a problem because it has fewer than T minus 1. Well, if it has fewer than T minus 1, we can now try to merge it with a sibling node there. And of course, we have to maintain that when we merge, we don't create more than 2 T minus 1 keys, but that's fine. Again, we can do some operations on this, some simple operations to resolve this issue. One major difference between deletion and insertion is that in insertion, we always insert the key in the leaf. When you are deleting, you cannot guarantee that because the key you want to delete might be in some internal node. So if you delete it from some internal node, it's not just about the T minus 1 might be violated, but now we have a problem because we had pointers there. So if I have, let's say, M, P, and R, so suppose I have 3 keys, then I have these 4 pointers to children, and if I wanna delete P, and I just say, okay, it's M, R, then we have something like this. But this is not acceptable either, right? Because now we have 2 pointers between M and R, and that's not allowed with the definition of a B tree. So this also requires a simple operation to fix it. And again, the full details of the algorithm for deletion and for insertion are in the textbook. The last point, and again, for the deletion as well, the running time is O of T log of n to the base T. The very last point I want to make, it's a point about efficiency in practice that is usually implemented. When I talked about insertion, I said if we insert a key in the leaf, we might need to split that leaf. If we split it, we might be forced to split the parent. If we split the parent, we might be forced to split the grandparent and so on. So the way that algorithm would work is that first let's go all the way down to the leaves, while every time we are doing a read from the disk. But once we start splitting, we are going up to the root and we are also doing write to the disk. A more efficient way is as we are descending from the root of the tree. So if this is the tree here, and suppose I'm going to insert somewhere here in this node. As I am descending, I first look and trying to insert the key, I look at the root and I say, where do I go? Suppose I want to come this way here. If the root is already full, just to be on the safe side, because I might later need to split it, we split it immediately, okay? So as I'm descending along this path, every time I hit a node that is full, I split it, okay? So I might need to split the root, I might not need to split this one, I might need to split this. The gain in this is that once we get to insert this node here, we insert a key in this node here, if I need to split the parent or a grandparent and something like that, they have already been split, okay? Now, of course, we might have done extra work unnecessarily, but these kind of data structures, we insert a lot of keys to them that eventually we will need to split these nodes, okay? So to summarize again, is that what I'm saying here is that the standard algorithm is insert the key in a leaf. If you need to split it, and just keep repeating. If you need to split the parent, and so on. But that implementation forces us to go down all the way to the leaf, and in the worst case we might have to go up all the way to the root again. This is too many times we are doing operations on disks. So instead, you can implement it slightly differently by saying that as you are descending from the root to a leaf, if you hit a node that's already full, it has 2t-1 keys, split it and go down. And as you hit nodes that are full, split them. Nodes that are not full, don't do anything about them. Once you insert the key in the leaf, then you will never need to go back up to do any splits anymore. Okay? So insertion and deletion again is about when we are inserting, we don't want to violate the 2t-1 maximum number of keys in a node, and it's always again the insertion is in a leaf. When we are deleting, we don't want to violate the minimum number of keys, which is t-1. We don't want to go below that. The other thing is that when we are deleting, we have to carefully account for the children pointers. So if we had 4 children in a node and we remove the key, that now will drop it to 3 children, okay? And we have to account for that. Both algorithms will take on the order of log n for descending down the tree and t times t, because whenever we are looking at a node, we need to do some t comparisons in the worst case there to find which child to follow.